Section 6.3, Taylor and Maclaurin series. Now, the definition here says if f has a derivative of all orders at x equals a, then the Taylor series for the function f at a is what we see down here. I'm not going to say all that, but there it is. And it says the Taylor series for f at 0 is known as the Maclaurin series. So the Maclaurin series is just the Taylor series centered at 0. So for all these a's, we would have zeros for them. That's what a Maclaurin series is. And that's mostly what we've been working with so far, at least for this whole chapter 6, is Maclaurin series, centered at 0. So now we're going to start building these series. That's what we're about to get into now. So the first one I want to talk about is the f of x equals sine of x. So now if you look at the formula here, I'm going to need an FA, f prime of a, f double prime of a, all the way to f nth prime of a. So we're just going to run through about 10 of these. I'm not going to go to n. N's going to be too long. But we'll go through about 10 of them. And it's nice to go through all these because then we get to really see the pattern. And that's what's nice about it. So I'm going to need a bunch of derivatives. So that's what I'm going to do first. So f of x is the sine of x. So f prime of x is going to be cos of x. Now what I'm going to do is I'm just going to keep going and I'm just going to write all these down so I don't spend 4 minutes telling you all these. I'm just going to put them all together now. So now I didn't quite get to 10. I got to 7 though. But I think with 7, I think that's enough to kind of see what's going on here. So now, and I also calculated the f prime of zeros because that's what we really needed for these. That's each of these pieces here. All the way up. So now, oh, I didn't do f of 0 for the original one. So I'll write that one down too. So f of 0 is going to equal 0. So I start off with a 0 there. So now if I'm going to just write all these out now. So the first one says f of a. So now that means that's going to be f of 0. So actually I'm going to write those out now with our formula. So there it is. So now essentially we can just plug in all of our values for those. And that's what I'm going to do now. And if I end up with a 0 on top, which we'll see here, that if I look at the double prime, that the double prime here is going to be right there, which that's going to give me 0. So I'll have 0 over 2 factorial. So I'm not going to include those values, but I'm going to include the other ones that are non-zero. Just letting you know so that when I rewrite this, you'll know where those components went to. So this is what we ended up with. So this sum here, now it's alternating. So now if we had to come up with the series for this, I could say n equals 0. And then I would go to infinity because I want to talk about all of it. And then if I look at each piece here, I see on the bottom that it's going to be like a 1 factorial here, 3 factorial, 5 factorial, 7 factorial. So if you look on the bottom there, that bottom is an odd number factorial. And how do we think of odd numbers? Now remember, the first thing I'm plugging in is 0. So maybe I can put in a 2n plus 1 factorial. And let's see if that gives it to us. So when I plug in a 1, or 0, I get a 1. So 1 factorial is 1. Okay, and then when I plug in a 2, a 1 I mean, that's going to give me 3 factorial. Yep, that would work. So that works on the bottom there. Okay, and it's just going to be a 1 on top. And then this x here, that x is going to be a 2, oops, n plus 1 as well. So let's try this. When I plug in a 1, I get an x. Plug in a 2. And I'm missing one component here. So I'm just going to kind of write it on the top here because I get this alternating sign. So first I get a positive. So if I'm doing n equals 0, I can just put an n there. So now that includes everything there. So that would actually be the series of the sine of x. And as I keep going all the way out there, that's what I'll end up with. So one more thing to consider here, since we were centered at 0, that means it was a Maclaurin series because they're centered at 0. And if you notice here, this is for an A in general. Ours turned out to be 0, which is good, and they're a lot easier to compute that way. We just find derivatives and plug in 0. That's usually pretty nice. So we actually found this series for the sine of x. What's cool about it is really this is just an infinite polynomial, which really violates the definition, but the idea of that is nice. So my numbers look like this, and if I had to do derivative of that, that would actually be very easy to do. So just something to keep in mind when we're dealing with these power series. One of the huge benefits is we can do difficult math very easily with them sometimes if we can get the Taylor series representations of them. So this would have been our answer for this one if we were looking for the Taylor series representation. So very nice, just using the formula.